Welcome back to our AP Chemistry Chapter 14 notes on kinetics. We're going to look in this section about the effects of temperature on the rate of reactions. So let's be sure we have a clear definition of temperature. It is a measure of the average kinetic energy of the particles of whatever we're measuring the temperature of. So the greater the temperature, the greater the kinetic energy. On average. There's always molecules with less than average kinetic energy. There's always molecules with more than average kinetic energy. But that's what temperature tells us, is relative to absolute zero, an idea of how much kinetic energy is in our system. So when atoms collide and they cause reactions to occur, when the collision is successful in achieving a reaction, that is because they had enough energy in the collision to make that happen. They had that activation energy. So we can totally get collisions between the particles that they just collide and bounce away, and there is no reaction because they did not have enough energy to reach that activation energy. If you'll remember our diagram, our energy diagrams has that hill, and if it doesn't get up to the top of the hill, it doesn't proceed, it just goes back. So they would hit, they'd bounce away, and there'd be no reaction. So roughly, temperature then can measure the relative ability of the atoms to react. At low temperature, we may have just as many collisions, but very few atoms will react. And at higher temperatures, of course, we'll have a lot more reactions occurring successfully, a lot more molecule collisions getting over that bump, regardless of how many of them actually are reacting. More of them will be successful. Now, we often show this information in a picture graph like this. So let's discuss what we are seeing here. We're actually seeing two lines graphed on the same graph. So we have in this case, red line that represents low temperature. And I want to point out, going from the peak down, okay, if that was a straight line, this is our average kinetic energy right there. So that would be the measure of our temperature. Let's say temperature 1. Okay, so at temperature 1, the average kinetic energy is that much. And we can see how kinetic energy is plotted right there on the x-axis. And fraction of molecules tells us how many molecules have that. So of course, the average is where you have the most molecules having that energy. At the higher temperature, we're going to have a similar thing happen. You can see how at higher temperature, we obviously have the average molecule at high temperature has more kinetic energy. So at temperature 2, or higher temperature, we have greater kinetic energy for the average. We still always have molecules with less than average. So there's like less than average there. And we always have, well, that didn't work, sorry. We always have molecules with greater than average. So over here, like in relationship to the low temperature, we have, all these with greater than average. The part of the greater than average that is of particular interest to us is this part here, this shaded region of the graph. We shade it to make it more convenient to locate. Did not have to be shaded. It does not have to be shaded. But it shows us if we integrate under this curve and we find the area under this curve, that would tell us what amount of molecules, check this out, have more than enough energy, that is the activation energy. Okay, so remember in our hill diagram how we have to have some activation energy to get up to the top of the hill. These are the molecules that have that much energy and will be successful in doing collision. What I want to point out is look at how small a fraction of the total molecules at low temperature this is. So what happens when we get to the higher temperature, temperature 2? Well, now we're shading the region under the curve, this new curve, and it goes behind the old curve. So that's why I'm shading over the old curve. Now we're seeing all these. What has literally occurred to the amount of molecules that have enough energy to get over the hump and be successful in making when they collide and successful in making a reaction, it is this amount, and that is a much greater area under the curve. So we see at high temperature, more molecules have the activation energy required to be successful when they collide. All these molecules back here are colliding, they just aren't successful when they collide. It's these that have the activation energy required to be successful when they collide. So at high temperature, we're showing how we have more molecules. Okay, we're showing we have more molecules that have the activation energy needed for successful collision. Sorry, to react successfully when they collide. Okay, so Savant Arenas, a good friend of ours who you might recall from pre-AP, you're like, why does that name sound familiar? Well, he came up with one of our definitions of acids and bases. But he did a lot of other chemistry work, and one of the things he did was calculate a relationship between the activation energy, okay, so that's this EA, and the temperature, and the amount of possibly productive collisions. Okay, so we have the temperature there, we have this possibly productive collisions going on there, and so K is our rate constant, and it's going to be important that you view this always, this chapter, as lowercase k for your rate constant. What are we trying to say? We're trying to say that the rate of the reaction is going to be some amount of, let's say, just constant that represents the fraction of the collisions that will have the proper orientation when all concentrations are 1 molar. That's a lot to say. It's some particular constant that would change for every particular reaction. But knowing it's the reaction of chemical A with chemical B would give us a particular A value there. We have our, then we're to check that out. We're going to subtract our activation energy and our R and our T. So we can answer some questions about this, and I do want to point out before we get going, which R should you use? Because there will be 3 R's on your formula chart on the test. Well, we are talking energy up here, so you better use the R that contains the joules. It actually would be joules per mole per Kelvin on your formula chart. That's the R value you want to use there. Okay. Well, so what I want you to notice is check out how activation energy is in the numerator and temperatures in the denominator. This could be very important because what do we know? If the EA is larger, if it needs more energy to activate, if that hill in our diagram is taller, I'm really exaggerating it, but you get the idea, then why is it going to be a slower reaction? Well, check it out. If this is bigger, we're subtracting more away from this, and K ends up smaller. And so we definitely get a slower reaction, and we can see that by this calculation, and we would be able to see that in a diagram, an energy diagram here, or hill diagram, and say, you know, it's going to take a lot more to get the molecules up that hill. So what does a catalyst do? Well, what did we say earlier about a catalyst? Catalyst does this alternative pathway, this tunneling, this lowers the activation energy, literally. So when a catalyst is present, what should happen to the EA? Well, the activation energy should decrease. That's the only thing catalyst is going to do is decrease the activation energy. If that decreases, what happens mathematically? Well, we're going to subtract less from A, which actually means K is going to go up. It's going to increase. So the value of K is going to increase, and therefore the rate of the reaction, it's going to go faster because EA is less. We're subtracting away less from this constant that we would know for a particular reaction. And so mathematically and diagram-wise, it matches. It works out. So why do we see this again? Well, now I want to talk about what a catalyst does. We've talked about the effect of temperature. Low temperature, fewer molecules have the activation energy required to react. High temperature, more molecules, all the area under that curve. Okay, so for those who are taking calculus, you could integrate that section. You would integrate it not from 0 to whatever. You would start here. But that would tell you the percentage of the molecules that have the energy necessary, the activation energy, to be successful when colliding. What does a catalyst do to the activation energy? What does the catalyst do to the activation energy? Yeah, I know the first time I asked you weren't really going to plan to answer. So hopefully you have answered now. What does a catalyst do to the activation energy? It decreases it. How would we show in this diagram a decrease in activation energy? Do I need to ask it again for you to actually answer? How are we going to show a decrease in activation energy? Well, hopefully you're like, well, more kinetic energy is more energy, so less activation energy would mean maybe we move the activation energy this way. I wish I could draw a straight line. So a catalyst would move that activation energy line to a newer, lower position there in the chart. So what does that do for us? Well, what have we been saying a catalyst does in general? Speeds up the reaction. Why does it speed up the reaction? Why does lowering the activation energy help speed up the reaction? Even at low temperature, look at how much more molecules have the activation energy required to be successful when colliding. Now it's this whole piece here. You can just kind of eyeball it, but that looks like at least double the amount of molecules when they collide will be successful. So certainly we'll get a faster reaction. And then if we do both a higher temperature and a lower activation energy, check out how much of this is going to have that activation energy required, right? So lots and lots of molecules are going to have the energy required to successfully react when they collide. And that's going to speed up the reaction. In this case of the blue, that chunk looks almost like maybe a third or at least a fourth of the entire curve is now past that activation energy line. So it would not surprise me if on the AP test they give you a diagram similar to this and ask you to, with one curve already drawn, maybe ask you to draw in another curve. They could ask you that. Or they could ask you to draw what would the effects be of adding the catalyst, and you would draw the line in there. Please don't go that way. Things like that. Or they could just ask you to analyze it, as we have also done. So hopefully you're understanding how useful, yet at the same time quite simple, this diagram is. There's not much going on, but you need to know what each part that is going on is trying to tell you. That is very, very important. Less important on the test, and I know you're like, well, if it's less important, why are you telling us? Well, I just want to make a point here. Okay, so bear with me for a moment to make a point. We have taken Arrhenius's equation and substituted, if you've got two equations, two unknowns, you can substitute in and combine them into one equation. What we've able to accomplish is this is going to tell us the rates, how they compare at two different temperatures. So at temperature 1, the rate 1, and at temperature 2, rate 2, and we'd be able to know, is it, by increasing this temperature, is it going to, double? Is it going to triple? Is it going to be half of what it was? That's what we would be able to figure out. So let's give this a try. The natural log of, now K2 and K1 is the two rates. And I'm asked for the change in rate. So I'm actually looking for that whole fraction. So if you don't mind, I'd like to simplify that to x. So now we're going to take the activation energy, 50 kilojoules, and we're going to divide by R. Now, which R do I need? Not the Pirates R, obviously. I need the R involving joules because I'm talking energy, and check out how energy is in kilojoules. So that should clue me in. Find the joules. Joules per mole per Kelvin. Now, did you figure out what I messed up with? We'll come back to that thought in a moment. If you have not figured it out, then maybe it'll come to you. What are two temperatures? And notice how it has to be in Kelvin. And you're like, what if I forget Kelvin? Well, your entire calculation is going to be wrong. I'm sorry. That's the way it is. So how do you remember to put in Kelvin? Check the label. Ladies and gentlemen, the label is your friend. It reminds you because labels always need to match in equations. This Kelvin would remind me I would need kelvins here, because if I had Celsiuses here, I'd be like, oops, that's not going to work. I need to convert. Also, hopefully you notice, check this out, that the kilojoules and the joules here did not work. So I need to convert either this to kilojoules or that to joules. I find it easier to convert to joules, so I'm going to just add 3 zeros there because we multiply by 1,000 and boom, we're done. Okay, so this is looking lots of fun, isn't it? Well, the fun has only begun because now it's calculator time, and I know you're like, oh, sorry. You're like, woohoo, yay, calculator. I was waiting to use my calculator. Well, rest assured, they are putting less and less emphasis of using the calculator on the AP test because what's it prove in the end? It proves you know how to use a calculator, not that you know what the chemistry is. Okay, so, and for some reason my calculator likes to make a chime. So anyway, 6,013, okay, 6,014, I'm gonna round it off there. Joules have canceled joules. I do have per kelvins going on there. Okay, and we do have a moles going on there, but we're not going to concern ourselves too much with that at the moment. I'll come back to that thought. So over here, we're going to simplify this. So taking 1 and dividing it by 300, if I can type that into my calculator for the right way, there we go. And 1 divided by 310, okay, we get 0.001075. And then the kelvins have canceled the kelvins. If you don't see it, prove it to yourself that it has canceled. So kelvins are now gone. Okay, and so when I multiply these two together then, times 6,000, and I've been keeping a lot of sig digs. I would be sure to round to sig digs at the end. I get 0.64, let's call that 67. Now I'm really not done yet. What do I know? I know the natural log of x is equal to that, but I want what the log, or sorry, I want what, without the log, the natural log there, I want what x is by itself. So what's the opposite of a natural log? The e, right? So let's e both sides. And I'm sure there's some fancy name for it, and I just don't know because I'm a chemistry teacher and not a math teacher, and I just really don't care, in all honesty. So if you know the fancy name for it, great. How do you remember that e is the opposite of natural log? They are usually found on the same button on your calculator. You might have to hit the shift button to get the e, or you might have the e be the button and you have to hit shift to find the natural log, but it is there together to remind you of that. So if you were asked to do this, it would not be something unheard of. Okay, and now I'm going to go to my sig digs, and we're going to pretend that that was 50 exactly, and that was 300 exactly, and that was 310 exactly. So I'm going to go to 2 sig digs. 1.9 is my answer. Okay, well, la-di-da, what does that mean? Because more than likely on the AP test, if they were to ask you a calculation like this, yeah, they want you to calculate. In fact, they want you to show the equation, show your numbers plugged in, round your answer to sig dig, have the right label on it, and K should not have a label. But what they do want you to do later, usually, like this is a part A and on part B, they want you to explain what does this mean. So let's ask, what does this mean? What were we looking for? Compare the rate at 2 different temperatures. How much temperature change? 10 degrees. So 10 degrees Celsius or 10 degrees Kelvin, because it's all the same in size. So with an increase of 10 degrees, the rate of our reaction has gone up by 1.9. In other words, it is almost doubled. And that brings us to our typical rule of thumb with kinetics. Not that you would want to answer on the AP test with this, but just in general, we normally consider for every 10 degrees of temperature increase, you're going to get a doubling of the rate. And we have just proved you don't quite get a doubling, you get a little less than that, but it's definitely close enough for this oversimplified generalization to work. Okay, again, It is extremely unlikely you will be asked to solve this equation on the AP exam because it proves you know how to use a calculator, not that you know chemistry. What you would be very, 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 very likely, it is extremely likely you will be asked to draw and or analyze a graph such as this and explain what a catalyst does or what an increase in temperature does or what a decrease in temperature does. Or even, I mean, they could get crazy one year. I don't know that I would expect this, but they could ask what an inhibitor does. Well, if a catalyst moves the EA that way, an inhibitor would move the EA that way, which then means you'd have less molecules having having the chance of reactions when they collide. So an inhibitor, as the name would imply, would inhibit or slow down the reaction, opposite of a catalyst. Okay, so that is very likely what you would be asked to do. Now this is rather interesting. If we take that equation and do a little bit of work on it, just some mathematical rearrangement, you can prove it to yourself that I took the old equation and rearranged it this way. We suddenly get it looking like a y equals mx plus b. So we not only could go with this graph to figure out what the change in temperature does, we could totally go with a graph that is made up of that. How would this graph look? Let me switch to a darker color. Well, we would have our axes, and our y-axis would be the natural log of k, lowercase k. And our x-axis would be the reciprocal of temperature. And our slope is negative. So I'm going to draw a line with a negative slope, and that's supposed to be a straight line. What is the slope? Well, the slope is equal to negative EA over R. So that's going to be a constant. Notice it was supposed to be a straight line, constant slope. What's going to happen when this slope crosses the y-axis? Well, that's our B, that's our y-intercept. That gives us the natural log of A. So if I had a picture like this, I could mathematically solve for what A is, or find it off the graph here. I could also be like, well, here's the reaction at two temperatures. At the lower temperature, the reaction is here. At the higher temperature, the reaction's here. What's happened to the rate? How has the rate changed? Okay. Now, did you notice? I said at lower temperature, it's out here, and at higher temperature, it's out here, because I'm graphing reciprocal. So 1 divided by a small number is actually greater than a 1 divided by a bigger number. Okay, so temperature 1 lower would be out there, temperature 2 there. Well, all we'd have to do is come over here and find K1, okay, rate 1, see what the old rate was, and then we can find K2, and by taking the E to that number and find K2 and see that would be our change in rate. So we really don't even have to solve an equation. If we make it into slope-intercept form, we can just get our information right off the graph. And this is also something they are more likely to ask than just grab your calculator and plug and solve. Okay, so what is the effect of temperature? The effect of temperature speeds up the reaction in almost every reaction. Of course, that's not guaranteed. Sorry, I'm going the wrong way. But you would need to be able to justify it with a diagram like this. In theory, you should be able to prove it by calculation, although this is unlikely to be needed on the test. And most certainly, you could be asked to explain it or justify it or find useful information from a chart of it like that as well. They're big into drawings, they're big into charts, so be sure you understand how those are used. Okay, so that's going to stop us with that section, and I'll see you next time. Good luck on your assignment.